So we have little rod CB that is attached by a pin connection at C, and at B that there's a pin connection with the spring. Okay, and we apply a force that we know of 100 pounds. That's the force P. So if we look at the free body diagram of the rod CB, what do we have? We have the spring, and remember a spring can push and pull, but only on the direction of the line of action. So we will have the spring, the force of the spring that is pulling at the point B, but aligned with this direction. At C, we have two unknown, because it's a pin connection, CX and CY. So you see the strategy there will be to do the moment about the point C. Sum of the moment about C equals 0, because what we have there is just P and the force of the spring. But we need to know some angles for that. Let's look at P first. That's the easiest one, I think. P, the good strategy will be to split P on this axis and this axis, because this one is going through the point C, so it doesn't create any moment. So we just need to know that this value of P, and for that we will use the theta there. That is 120 degrees. So if this one is 120, so we have 120 like this, okay, we have, let me try to just make sure that I explain it correctly, but this is 30 degrees there, and the total angle there will be the 90 and 60, but this one will be 30 degrees too. Okay, so for the moment about C, if we look at just the complement P, this one, that tend to rotate in the negative directions, we have the P cosine 30, so just this complement times the distance L, and it's rotating in the negative directions. Okay, so that's for the P. And for Fs, if we look at Fs, so we have Fs, the force of the spring. So we should split in two components, one perpendicular to the rod and one parallel to the rod. So the only component that creates rotations about C, a positive rotation about C, that's the vertical component. So that's plus the force of the spring sine alpha times the distance L, it's equal to 0. Let's look at what we have, what we know. Okay, let me put in blue what we know. We know P, it's 100. We know L, it's 1 feet. We know L. The final question of this problem is to find K. So to find K, we need to find the force of the spring. And so we don't know the force of the spring, so it's a red one. And we don't know alpha too. Okay, so let's work on that. Alpha. Oops. Let's look at this triangle. Let me make it there. Okay, let's look like this. We have 120, we have L, and we have L. So that's an isosceles triangle. That means that both angles are the same on both sides, alpha, right? So we have 120 plus 2 alpha, that is equal to 180. This is the total of the triangle. So we got 2 alpha, that is equal to 60 degrees. So alpha equals 30 degrees. Okay, that's awesome. Alpha now it's a blue value. 30 plus 120, that's our 180. So if we look at, so we can find Fs. Let's find Fs now. So we will have it. Okay, so we have the force of, the force of the spring times the sine alpha times L, that is equal to P, that is 100, cosine 30 times L, that is 1. So we have the force of the spring that is equal to 100 cosine 30 divided by the sine of 30, and L, that's 1 also. So we have just 100 divided by tangent 30. 100 cosine 30 divided by sine 30. 173. So the force of the spring is 173 pounds. Okay, cool. Now the question is to find K. So what is K? Let's write it there. We have the force of the spring that is equal to K times L minus L naught. So we need to find L and we need to find L naught. And we didn't find them yet because the only thing that we know for now is Fs, and the final question is to find K. So we need to find a way to find L naught and L. Okay. Oh, L and what I call L. Let me call that L1 because it's confusing with their L. It's this one L. This L1 from A to B. Okay. So we have this triangle. Okay. The same than before. Let me make it again. We have the 120. This one is 1. This one is 1. And this is 30. And this is 30. And we are looking to find L1. So we can use the cosine law for that, right? So we have L1 square that is equal to 1 square plus 1 square minus 2 times 1 times 1 times cosine of the opposite angle, 120 degrees. So L1 is equal to the square root of 2 minus 2 cosine 120. How much is that? Square root of 2 minus 2 cosine 120. That's 1.73. Okay, so we have L1 and now L naught. L naught, the information that we didn't use there yet is this one. We know that the spring is unstretched when theta equals 90 degrees. So that means that we have this little triangle, and this one is L naught, 1, 1, and 90 degrees. Okay, so that's the hypotenuse of a square, like not a square, but half of a square, like a little isosceles right triangle. So L0 square, L naught square equal 1 square plus 1 square, the Pythagorean theorem. So L naught is equal to the square root of 2. That's 1.41, 42. Square root of 2, 1.41. Why did I put a degree? It's not a degree. It's, if L is in feet, this is in feet too. This is in feet too. Okay, now we know L naught. We are almost there. So let's take this, oops. Let's take this equation and let's use it there. I have a little bit more space. Okay, so we have the force of the spring, 173. It's equal to K, the unknown, time L1, 1.73, L naught minus 1.41. And we get K, that is equal to, let me use the exact number, this one, divided by the 1.73 minus 1.41. 545. And that's pound time inches for this one because, oh, time feet, sorry, because I was thinking about another problem that I just made. 545 pound time feet because that's the unit for this problem. There we go. Let me highlight the final answer. So one step at a time, and use the right equations to solve for the unknown that you need. We just need the force of the spring there. We don't need the reaction at C. So let's do that and see how you can split your component to have always one component that is going through the point, so it doesn't create any moment. That's always much easier. What we did with those two purple components and those two green components. we try to use the axis BC to avoid to have two moments for the two complements. See you in the next video. Bye bye.